The content of my talk is Introduction to Hyperband System and 8 remarks on worldwide survey. I would like to acknowledge Dr. William Pather because I gone through so many articles written by William Pather, and I will introduce the initial antenna developed by our laboratory, that half TM horn antenna, and the silent contribution of STM antenna and its parameter calculations. Then I will compare with the STM horn antenna with the folded feed half impulse radiating antenna, and I will show that what is the advantages and disadvantages of these antennas over the STM antenna. Now exactly I would like to also explain that how the pulse get converted into the radiations when we are feeding some pulses which has some durations, rise time and width. So how it will convert into the radiations, and that type of the mathematical aspect I will explain it. Then all the parameters of gain feed impedance by using simulation software, CST Micro Studio, and conclusion future scope. So this is the basic block of our system, that HVDC power supply is there, that is about 30 kV DC source is there. Then we are feeding to the mass generator, generating a 600 kV altitude of the amplitude of the voltage pulse, and that pulse is fed to the picking stage spark gap and then fed to the different types of antenna. So initially we develop a half TM horn antenna, that is complete of half nature is a ground plane is there and tapered plate is there. Then I observed so many results based on this STM horn antenna, and we developed some new folded feed antenna. That entire geometry and work is supported by the Carly-Baum's notes and our chair's notes, and that is measured by our own developed sensor, that TM sensors are there, and we use some good calibration equipment by Tektronix provided by DPO 410B oscilloscope. It's having the 5 giga samples, so that also this cable is treated by properly, so to get proper readings. So and the entire, this is a block diagram of our system. Now also I have some background of this system which is developed in our laboratory in ISC Bangalore, LRD, DRDO Bangalore. So this is the only for the test purpose which is developed in the laboratories of having the SF6 gas switch. It's inside this switch is there. So this switch is inside this ROM, and this switch is fed by the gas of SF6 by using this line, and then fed to the antenna. And these are some resistive load to match the source with the load to have the maximum power will be delivered to the reflector. So these are the source, and it is the only lab-based system. So now in our laboratory APPD BRC, we also develop compact half TM horn antenna, and the entire capacitor bank, there is a mass generator system, is we packed inside the 1.5 meter height solid tank, and at the top here is a picking stage is there. It is called picking spark gap switch, and this picking switch is really working well, and the modeling and entire domains we do it in PIC modeling, CST magic software, PIC code, and then whatever the result, whatever the experimental output we got is fed to the half TM horn antenna. So this is the ground plane is there, and second one is a tapered plate. So this plate is terminated by load, which is having the copper sulfate load, which is very, very low inductive load. And if you observe this picture carefully, so it is a spark gap switch having the Rogaisky profile in nature. But initially we faced some problem that spark gap and mass tank is at the same pressure. So because of this same pressure, this capacitor tank will not able to handle 2 kg and more than that pressure. So that's why we modified this picking stage, isolating the pressure arrangement. So there is one knob is there which is for the pressure arrangement, and this knob is for tank arrangement. So this compact new developed picking stage can handle about 14 kg per centimeter square pressure, and we also tested for hydrogen gas and so many different gases. So initially rise time was very, very low, it's only 6.02 nanosecond. To convert it into UWB system, we need some rise time which is in the sub nanosecond about or it's in picosecond. By using this antenna, we achieved 5 kilovolt per meter electric field intensity at 15 meter distance. So, but this system is not really working well. So we started work and gone through the so many articles written by William Pathurst and Carly Bohm's. So this is Carly Bohm's notes on low frequency comparative systems, and these are the feeding back to the resistive load because of this is the direction of the current, so that we will cancel out the backside radiations, and these are some mathematics work over here. So after doing a significant analysis on the STM horn antenna, it is observed that there is significant backside lobe radiations. So it is coming, playing a major role, and so directly affecting the front side radiation of the antenna. Also there is a side lobe radiations from left side and right side. So also that's why the gain is never crossing the 0.5. It is gain is calculated by using this formula, is RE far by V peak. So that's why the problem we are facing, that how to improve the front side radiation to make a directive antenna, how to change the peaking stage arrangement, everything we started newly. And these are the comparison with our CST simulation software with the experimental results. So I really thanks to CST because their results are approximately accurately matched with the experimental results. And our sensor also, we are using some B dot sensor initially. Then we develop our own TM sensor for the calibration purpose. Now this is for the without peaking stage, a pulse. When a capacitor is discharged, there is no peaking is there. So after putting some peaking stage over there, this rise time gets sharp over here, and the amplitude is very, very high, about 264 kV, and pulse duration is 300 nanosecond. Because of capacitor tank is about 1.5 meter height, and that's why the duration is there pulse. So by using a peaking stage, we improved the electric field intensity 3.5 kV electric field intensity, which is not 0.5 kV when the peaking stage is not there. So in this entire block diagram, the peaking spark gap is a very, very important, playing a very important role, and we are mainly concentrating on that side. So myself reported one article on this, and there is so many points also there in this article, which is published in 2013. Now after doing a theoretical and experimental and modeling simulation analysis, it is observed that we need to change this TM horn antenna. So also I gone through the article written by Dr. R.T. Lee and so many authors, that the characteristic impedance formula is this is not without feeding height. So this feeding height is a very important, which will directly affect the characteristic impedance variation. So I completely modified that R.T. Lee's formulas and reported over here. That is this is the new mathematical formulas, and which contain the feeding height, because feeding height are very, very important. Well, because of this, because we are playing with a high spark gap, high amplitude spark gap. So this ground plate and this taper plate should not short. So it ideally, mathematically we say it is a short, but practically it is not possible. So that's why there is some feeding height is there. So this feeding height factor is coming over here. So this is the new formula, and that's why the plots are different for the different mathematical equations. Now we propose the same antenna which is developed by the Carly Bohm and our Air Force Research Laboratory in New Mexico. That this antenna is without feeding height, so there is some angle also there, launching angle is also there. Now this antenna is having a vertical feeding arrangement, and is terminated by the non-inductive load to the reflector, and we observe some the feed factor. We are concentrating on the field factor of the reflector. So field factor is that how uniformly you are distributing the feed on the reflector, so that we will get the back side radiation, front side radiations. So without this, if you observe carefully over here, this is a straight arm is coming. So straight arm is not that much actually, but it is like a something angle is there is forming because of the width of this arm. So after doing a modification, we change this tapering to the in the arc curvilinear nature. So this curvilinear nature will directly improve the uniformity of the field on the plate. So we got a more uniform field on the reflector. It will directly focus the maximum feed in the front side at the bore side of the antenna. So this improvement is mainly because of this folded feed nature, and this is some launching angle also there, that is called beta. So this launching angle is very important, because we are launching feeding the pulse to the arm and terminating to the match load termination. It's about 180 ohm. So that's why the arm nature is there, and the uniform field distribution is called field factor we improved by 1.2 factor. So it is directly affecting the electric field intensity about 14.4 kV. So this is the improved electric field intensity. So I did a test for the three different types of the model. This is the first one, which is without folded feed. Second one is a with folded, and third one is a parallel plate. So this is a parallel plate. This will directly block the your electric field intensity. So this is also the wrong way to do the design. So the best design is this is the best one design. Have the arm in the transverse in nature. So it will avoid the blockage of the electric field intensity, which is heated on the reflector, and the arrangement should not like this. So all these comparisons are there: HRA1, HRA2, and HRA3. These are the half impulse radiating antenna, half impulse radiating antenna third, and one. So second one is the good results I got by using the modeling results. That's why I proceed for the experiment. Now in that system, initially the picking stage is not at the same pressure, because capacitor and picking stage are the same pressure. So that's why this picking stage need to be modified. So this is the newly modified picking switch, which is placed inside the mask at the top of the mask tank, and this arm is coming out. So this arm is fed to the launcher or feed arm of the reflector. So this indicator is for the mask tank, and this is some another arrangement for the switch. So there is different pressure in between them, and this is the AutoCAD drawing of this switch. We are feeding some gas pressure from the upper electrode. So if you observe carefully, here is a small hole is there. So this hole is for the inserting some gas inside the chamber of the switch, and we played about 15 kg per centimeter pressure, and we also thinking about the 80 atmosphere pressure in the next experiment. So initially the mass tank is about 0.5 kg per centimeter, and new picking stage is 2 kg only. So that time this is the bandwidth of the oscilloscope, and we obtain results about 1 nanosecond rise time, and these results are significantly getting some oscillations initially because of some inductive parts is playing inside the switch. So that part also we take care, and we observe carefully. It is 966 picosecond rise time is there. So the initially rise time was a 6 nanosecond. Now by using changing the picking stage arrangement, spark gaps arrangement, we obtain the 966 picosecond rise time. So this is the approximately 1 nanosecond rise time, and peak amplitude is 250, and the pulse duration is 300 nanosecond, because mass generator is 1.5 meter height. So entire discharging process is there. So this is the developed experimental arrangement, and we conclude over here is that the experimental outputs pulse from the mass is 0.5 kg, and picking stage is a 2 kg pressure. We are getting very interesting results. These are the separate arrangement for the tank pressure and picking stage. This is for tank pressure arrangement. This is for switch arrangement, switch pressure feeding arrangement. So this is separate isolation system. So entire setup is we develop, and this is a terminating resistive load. It's having a very low inductive in nature, so that will avoid the ringing effect on the observation. So these are the sensors calculations, because we are using a sensors which has some effective height of about 12.5 meter millimeter height, and this oscilloscope reading is V oscilloscope is 90 volt. So E far field calculation is based on that, and these are our own developed TM sensor. So these sensors are really working well, and we have got final E far field intensity 14.4 kilovolt per meter at a 15 meter distance from the center of the source. So this is the results. Okay. These are the only 5 degree direction from the front and back side. So we got a very directive antennas. If you observe, it's a minus 5 degree from the bore side. This is plus 5 from the center of bore side of the antenna. So these are the results, and these are the certain. This is a sensor arrangement and picking stage arrangement. We are thinking of designing some anechoic chamber to get the more accurate results, but we did a result last time in the free space. So this is a comparison, and if you observe over here, it is a very good results at 15 meter distance, and I'm afraid about why this gain factor is less than 1. So these are some newly analysis which already I reported in my articles. Now I would like to conclude over this, like in this project I extensively work on mathematical modeling, then simulation, then experimental work I did in last 3 years. So in 2014 in MRM conference I reported only the mathematical part. Now I am presenting the mathematical simulation and experiment also. So these are the all important points which already I highlighted. Also I would like to contribute this feeding height is a very, very important part while designing the STM horn antenna. Now also these are the some important results which are obtained from the our system. It's 14.4 kilovolt electric field intensity at 15-meter distance. So this is the one of the good radiator I can say, but it's not comparable with the Jolt system, because Jolt has a very, very high, very, very low rise time, and that system is operating at a very high intensity of pulse. So I would like to perform some future scope applications where this STM antenna performance can be improved by putting a dielectric lens at the aperture. So dielectric lens is important. The launching pulse characteristics are also important, because we are feeding some pulse to the arm and that pulse is launched on the reflector. So we are coming back, so this launching pulse calculation is important. Also mass hyperband system can be used for the application like a study of shading and everything. So these are the important, and how to classify the malfunction and destruction of the electronics. So that malfunction will automatically reset our electronic system, but destruction is another system. So there is so many articles which are already available on net, planning to submit. I would like to special thanks to Dr. Devgiri and William Pathers and Dr. Everett ADL Shamlagu. These are the papers I take from most of the papers from them. Also special thanks to Carly Baum. Because of that notes available on the website, I did some good work, and these are some advisory committee from India. Okay, thank you.
Is there a quick question? I think in the interest of time, what we'll do is if you have any questions for Dr. Umbarkar, you can catch him after the meeting and ask him. He'll be around. And this will be the last paper in this session. I'll turn it over to Dr. Koshlev for TC11. Thank you.